Imagine you're in an era of seemingly infinite inventive possibility. Lots of things are ahead. You can create anything you want. There's new hardware that's come out that's smaller and faster. On top of this, we have powerful languages that are giving us the ability of creating fault-tolerant, amazing devices that we'll use to be able to drive our innovations forward. During this time, we've also experienced a situation of connectivity. I don't know if any of you have experience in this realm, but bulletin board technology comes out, connecting people together, giving them the ability of sharing information. Moving on from there, we have the internet taking hold, getting us 500 free hours every week in the mail for a decade. And during this time, this spark that happens starts to drive more and more people towards the web. This connected place, more people are coming online, so more developers are joining the community to be able to facilitate new, innovative ways of creating these digital landscapes. And then something happens in this realm. Well, things get a little bit easier. Some players come into play that offer tool sets to make this a little bit nicer. You have Rails. It enters in a new era of developers. Suddenly, we're flooded with all of this, we flooded the space with all of these new people that have creativity. And Web 2.0 is born in case. We've rewritten the internet, and we were okay with that. Moving forward now, the landscape continues to change and connectivity lines start to get blurred more and more. Enter Phoenix and its channels and sockets and real time. We're starting to now try to bring the web together back with those devices that enriched our lives. But what happened to those devices? To me, it doesn't seem like a lot changed. I mean, here you have a credit card processing terminal on the left and you have a credit card processing terminal on the right, both with magstrip technology still hanging onto them. It seems like during this time that the web was having explosive growth, hardware developers were concerned over how rounded they could make the corners on these devices. Well, it seems like there's a lot of problems that need to be tackled in this area to be able to give us the ability of pushing the design forward again. One of those is the ability for us to rapidly prototype these kind of concepts and ideas. So here's a quote that I've got from a colleague of mine, a company called Element ID. I need an embedded system and I need it in 1 week. Now this was said to me 1 week ago. I thought to myself, sure, it's not like I have a conference to prepare for. Well, after putting down a lot of work on some projects that I was invested in, I decided, sure, I'll do it. I'll take that job. I'm crazy enough to do that. And a week later, we were given this, fully 3D printed case and all. And it was actually kind of enjoyable, the experience. It didn't feel rushed. And it was the first time where I felt like I delivered a project that was, dare I say it, on time? Well, they were ecstatic. This is my brag slide for now. They said that we were able to deliver a production product, tested, out the door in 5 days without sacrificing performance or reliability. I was like, that's a fantastic quote. I have to put that up there. But he went on. On top of things, we've sort of created a landscape for them to be able to make updates to the device easier for future. Usually when you get into this realm, you've created this complex device. It's really hard to do. Well, how did we do that? With 2 web developers in 5 days. That kind of rapid prototyping is really what the industry needs, and that's Nerves. So what is Nerves behind the scene? Well, it's a team of extremely passionate people about rewriting the concepts of embedded system development to make it easier for and more attainable for developers, all types of developers, to have the feeling that they can create embedded hardware. So what exactly is it? Well, it's easily broken down into a group of about 3 different categories. We have a collection of frameworks. We also have a platform that we build on top of. And there's also a suite of tooling that we use as well. So that seems pretty easy. Well, what are underneath the covers of all of these? Lots of stuff. Fun goodies for everybody to be able to play with. To break this down a little bit easier, the frameworks are just libraries that you can use in your embedded projects to get you working with different things like LEDs or different ports. Our platform is a collection of systems that we've generated to run on all types of different target devices, Raspberry Pis and BeagleBone Blacks. We also have the suite of tooling, which is a collection of utilities and mixed tasks that'll get you to the point where you're feeling like you can get up and running easily. Now, this seems like a lot, but bear with me. It gets a lot easier. Here's a list, by the way, of some supported targets that we have for today. We've collected a bunch in the top there. That's pretty much all of the original Raspberry Pis, the A+, B+, the Zeros, the Pi 2, Pi 3. We have a collection of other great prototyping boards as well. And it doesn't really just stop there. We're extensible in a way that allows us to create on top of pretty much any number of Linux single board computers. And because we want this stuff to get smaller and faster and more connected, we're also looking to be able to integrate some smaller devices. You might be familiar with the chip. That was the world's first $9 computer before Raspberry Pi ripped the carpet out from under him and said $5. We also have a product here from Seed Studio. It's called the Linkit Duo. We're working on bringing that up too. It's a very small device in person, and it's got built-in Wi-Fi. These tiny little MIPS processors in them have enough space on us to be able to run the entire Erlang VM, Linux, and your application. So how do we do that with just a small collection of frameworks, platform, and tooling? Well, the first thing I want to show you is an easy way to be able to transition into getting started. And what we mean by that is everybody wants to be able to play along in the sandbox. So a sandbox to us is a way with the most minimal steps to provide an environment that will give you the ability of accomplishment without having so many variables to go wrong. And I mean by that, with a Raspberry Pi, you can use a Raspbian, which is the operating system that typically ships with that. It's a form of Debian. And everybody knows with working with Linux machines that then at that point you just plug it in your network, shell into it, and everything's good to go. Well, here's a small laundry list of things we have to do to be able to get this one running. We have to get the system updated to make sure that we have the latest kernel, establish a network connection. Then we can SSH into the box. Then we can install Erlang. We can actually use the ESL, Erlang Solutions, was kind enough to be able to update their Raspbian repositories for us. Then you can go on to install Elixir. Finally, you can check out our Blinky code. Blinky, by the way, is the hello world of hardware. And then at that point, you can finally run your application. All of that so you can blink an LED light. It's amazing. And from there, you can check out some of our example code to get it running on the sandbox. So this seems like an easy place to get started with the frameworks, but, well, what are the costs associated here? The sandbox weighs a lot. I mean, a Debian installation, you're talking about 600, 700 megabytes. It's going to take a while to boot to bring up the entire thing, about 30 seconds or so. Updates are going to be happening through some package management utilities, and it'll be a little hard to be able to remotely monitor or control. And reproducibility of this system is low because, you know, you could have the package updates happen in one area and they get a little bit further along in another area, and then you're out of sync in these systems. You don't really know what software is on what, and if you have 100 to 150 devices distributed, it becomes very difficult for you to be able to synchronize this kind of stuff. Well, there has to be a better way. And there is. And that's the platform. So once you've experimented with the frameworks, and you may have something working on your device, now you want it to be a little bit more distributable. So what we do is we build our platform on top of an opt-in approach. We use build root underneath to be able to create a lean but robust enough that with everything you want included system that you can attach your application in Erlang to, and then it'll give you maximum performance and distributability. So what does that look like? Well, we've taken that size down a notch. You can ship the entire Linux operating system with build root on our systems and your application and the Erlang VM in about 20 megabytes. It boots in about 4 seconds. The entire update is the entire firmware. It includes the entire subsystem as well. So if you need to be able to make an application change that requires you to install additional Linux configurations, that gets versioned along with your application. Reproducibility is high because all of our scripts and systems will build the same way from our configurations today as they will tomorrow at that version. And volatility is low. And what I mean by that is, in the case of the full-on Debian installation, read-write is happening all the time. And these devices are booted off of SD cards. And I'm not sure, but if you take a power plug and unplug it while an SD card's being written to, you're not going to have a good day most of the time. What we do in our systems is we actually reduce the volatility by making your file system read-only. This doesn't sound good right now. I know the first time I heard it, I was like, It gets better. So we wanted to make this easy for people to use because there's a lot of complexity in the amount of services that Nerves is. So the first idea that we had was, well, you can only actually build systems using Linux hosts. Build root only really runs on Linux. But as I've seen from the sea of developers in this conference and most others, there's a lot of people that use machines other than just Linux. So our first answer to this was to create a service we were calling Bakeware. And we were like, oh, let's make it easy. We're going to be able to build it somewhere else. We'll ship you a cached version of it. All you got to do is install this utility, create this thing we were calling a bake file, then do these commands that you'd be like, get the system, and then get the toolchain, and then bake the firmware, and bake burn, and you'll notice that none of this felt like what it felt like to create other Elixir applications. Nowhere in there do I see the word mix. And so it wasn't until one day when Jose called me up and he said to me, tell me about this bake thing you're working on, that we actually had to question what it was. Because it should be easier than this. This was even too difficult. It was hard to maintain. And in reality, when we were working on Bake, it just kind of felt like we were reinventing Mix or trying to do Hex again or something like that and handle it on our own. And it didn't make sense. But we needed to be able to open the conversation so that we could integrate ourselves to make it even easier for developers to get started on these. So we turned this into this. Starting today, you can now completely use Nerves from within Mix. It acts like any other application and exposes several commands that we added in for you to be able to export your project to your device and run it. All you have to do is fetch your dependencies and mix some firmware. So how does this work? Well, behind the scenes, we have your application. And your application might consist of some Elixir code, and you might have some C code in there. You might have some NIFs and ports if you're using something that might have to reach in to do some crypto or something like that. And when you compile all this stuff down, typically, you compile it on your machine using Mix. And all this stuff gets fed into the Elixir compilers, and it gets mashed up together. And on the output end, you get some beam files and some binaries with your compiled C code. And voila, you have your application specifically compiled for the machine you're running on. Completely different than any other architecture, because of that binary code that's included in there, those dependencies have now been compiled down to only run on that machine. So why did it make sense to make bake? Well, bake allowed us to be able to take mix and just go, I'm just going to wrap around it. And that gave us ultimate control over being able to reroute the requests that you were making to compile your code to ensure that it would actually run on your Raspberry Pi 2. This was a big requirement for us because we needed to be in charge of, at the time when Mix asked, called out to the environment for who's the C++ compiler or who's the C compiler, that it actually went to the right place. Because we don't just support Raspberry Pi 2, we support all kinds of target architectures. So let's look into this a little bit further. Well, under the hood, what we were doing is you fed in a target and you said, Bake, I want to build for Raspberry Pi 2. And Bake would go, all right, cool. You know, I got the toolchain and the system here. The toolchain's going to be able to give us the ability of cross-compiling. The system's going to be that platform we build on top of. And I'm just going to feed those into Mix the way I need to. And out comes the other end, your application for the Raspberry Pi 2. Well, right here is where we saw it. We're like, well, why do we need Bake? Why can't we just have Mix? It needs to just be simpler. And the way that we handled this was at this point, we needed to be able to sort of invent a phase that happened before any of your code was getting compiled. We needed a pre-compiler step that allowed us to bootstrap the Mix environment. So if any of your application dependencies start compiling, or your application itself, and it contains C code, it's compiled using the right environment settings. And this is tricky, trickier than you think, because oftentimes, because we want to use Mix, oftentimes the toolchains and the systems are actually included as dependencies in your project. But we don't know where they are. So if we start loading dependencies, it starts compiling dependencies. And if we start loading dependencies trying to find who's the system in the toolchain so we can set up the paths right, it's already too late. You've already started compiling stuff, and you're compiling it for the host. And oftentimes, compiling these things that exist on the target might not work on your host. So what are these things here actually? And why is it so difficult? And why is it so important? Well, let's start with the toolchain. Our toolchains are built on top of a configuration you feed into it. The dependency is basically a tiny little configuration. And it's built on top of CrossToolMG, giving us support for running on Mac OS and Linux and soon to be Windows. There's a few namespace length pathing problems we're having there. It's built for the target, and it has a host configuration. So a toolchain basically is a series of compiler binaries that are built to run on your host, but they're made to compile for a target, like a Raspberry Pi. And so we feed that config into a compiler, and out of the other end comes quite a large collection of files, like 100 and some odd megabyte collection of files, that is specifically intended to run on your machine. Now we cache all this for you, because toolchains don't update that often. When you download a dependency from Hex that has the toolchain config, we already know everything about what it is that you need. So we have a series of HTTP mirrors in place that allow you to fetch down the actual compiled binaries for this, making it lightning fast during the process. What does one of these look like? You don't really have to worry about it, but they're all exposed inside of the configuration. If you're ever curious and low level enough to be able to try to figure out if something is enabled in GCC or what version it is that's running, you can dive in and take a look at the toolchains. It's part of the dependencies, just like any other dependencies you'd bring into your Mix project. So on the other half of this equation, we have the systems. Systems are about the same thing. The distributed dependencies that we have are the system configurations. And these, like I stated before, are built on top of build root. They use an architecture that's known as a def config. And that's basically a configuration that then gets compiled down into a real config. And in addition, it's a collection of root file system additions. Let's say you turn on WPA supplicant to be able to do some Wi-Fi. Then you need to include some files or configuration files in like Etsy on the host or on the target. Or you want to put some additional binary files on your system as well. Those are the root file system editions. And we basically, through the Elixir compilers for nerve systems, turn those configurations into systems, which weigh equally large, 80 to 90 megabytes in some cases. And so we do the same thing. We have a series of HTTP mirrors in this case that allow you to be able to download these precompiled systems so you can start building on top of them. Now this is where it gets a little bit trickier. In the case of the systems, we offer a minimal install images that allow you to get started to putting your application on. But sometimes you want to enable other things in the file system, like maybe you want more enhanced shell or some additional utilities. As I said, this is an opt-in approach that we take, so it's extremely stripped down to be able to run. Well, you can do that by editing the def config. Oop, wrong one. That one. You can do that by editing the def config. You can add additional packages. You can also, if you're familiar with BuildRoot, gain access directly to the screens that allow you to be able to enable or disable other utilities inside your application. But as I said, we include a lot. So we include Wi-Fi, we include things like that, networking that allow you to be able to get up and running quickly. Typically, you won't have to be able to dive down into this level. But if you do, you can certainly edit a configuration and create a new system. So that's what brings us back to this portion here. Now we know what's happening under the hood with Mix. We can see that the tool chains and the systems are in place for us to be able to, when Mix goes to compile our assets, point to the right places and structure it together with the right version of compiled Erlang and also with the compilers to create your code. But let's take a look at the path that we took to get here. Well, it's important to think about Mix as far as the life cycle is concerned. When you fire up Mix to be able to start executing commands, what we do at the time of precompile is we bootstrap things. This is where our bootstrap utility comes in place. When we call into the bootstrap at precompile, which is any time that you're asking to start compiling dependencies, we first make a call out to say, where's the system? We're guaranteeing that if you have a nerves application, there's at least the dependency for nerve systems present under the hood. Once we've identified that that's available, we then look at the rest of your dependencies and identify the other components that we're interested in. Nerve system contains all of our compilers. That knows how to turn the configurations into the actual product. And under the hood, you have your dependencies that say, oh, I want to be using for nerve system Raspberry Pi 2, and that system is built on top of BuildRoot. All you have to do is include Raspberry Pi 2, and it does the rest for you. So how do we do this? Well, for more advanced users, when you start creating new systems, we look for any dependency which contains this nerves.exs file. It's a special file that we've included in our dependencies that allow us to be able to, at precompile time, determine which one of the dependencies on the system are actually relevant to us. So we can put the right pieces in play without having to compile any of them, because then it's too late. So from here, what does this look like? Well, now we've identified things, and we're going to go in to start loading code paths together. Well, once again, we call into the nerve system to be able to make the identification of that system, and that system as a dependency of your toolchain and the rest of it. So we know now, and Mix can go on to compile your application. We've already bootstrapped the environment, and everything's ready to go. And because of the steps we've taken here, we're able to always ensure that your code is always compiled for the target. So it's important that you have the bootstrap piece in place. And as of today, we have the world's longest URL that you can go and install the archive. It's very lightweight, it's small. All it contains is the information required to be able to bootstrap your environment. In addition, it contains a new project generator. Getting started with nerves is now easier than ever. You just call into mix nerves.new, create an application, and pass it a default target you want to start using. And from there, everything is downloaded and ready to go on your system. So let's look at some of the magic under the hood that's required to be able to do what this does for you. Let's start with the mix file. The first thing we do is we try to gain access to what you're interested in using for a target. Now, out of the box, Nerves supports the ability for you to use multi-target. So if you want to develop an application that you want to both run on Raspberry Pi and BeagleBone Black, you don't need two code bases. We'll handle all the switching behind the scenes for you and ensure that when you tell it what target you want to deploy for at that time, that we choose the right system and toolchains for you. This is actually passed in from the environment, so much like how you'd use mix environment, you'd pass in nerves target, and the nerves target will let you change on the fly, but you can also set a default for your project as well. That's where the target flag comes from the new command here. Further in, we extended the project configuration. There's been some new additions to Elixir that allow us to be able to specify required archives. And we can see that we require Nerves Bootstrap to be involved. This gives users a pretty error message that asks them to please install that Nerves Bootstrapped archive so that things compile correctly. We also require that you expose the target to the project because we use it later down the line. And to be able to do all the magic behind the scenes, we supply a group of aliases that allow us to be able to patch into the right places for precompile and load paths. From here, we do a little magic, and we allow you to be able to use any one of our targets with a single line. The reason that we split out the systems, in this case, if I go back to this one here, you'll see that the dependencies are brought in, concatenated with a system call. The reason that we do it this way is because there should only ever be one system present at any time. So for handling multi-targets, you should never bring your dependencies for two different systems in together because the Bootstrap utility will get confused on which one you're supposed to use during that time, and that it'll only be able to have one present at any given time. So by switching targets, we automatically switch systems, and in addition, we automatically organize your dependencies and your build tool, or your build products by target, so that we leverage the caching of the tool set. So when you switch between one and another, you don't actually have to completely blow away all your dependencies and refetch, and completely blow away all your intermediates and rebuild. Everything will be cached and ready to go super fast for you. So we go on from there to be able to allow you to do some advanced configuration. You can, in your configuration file, you can actually import specific configurations for targets. This is important when you use utilities like our LED classes for frameworks. You want to be able to make it so that for the Raspberry Pi, you specify where the LEDs are on there, but for your BeagleBone Black, you want to specify where they are on that one. And that'll allow you to be able to import the correct configuration for the correct target. Changing targets is easy. Like I said, you can switch it at the command line. You can pass whatever you want. Then you can set it permanently for your session. If you only own a Raspberry Pi 3 and you always want to be compiling for that, you can just set that I have a Raspberry Pi 3, and every single time you download an example application or somebody's Nerves project, it'll automatically start compiling for your target to get it running for you. In addition, you can set it in the project-specific one so that if you want to just call mix commands directly without having to override, that project will be for that target. So here we are. We compiled our application. We're ready to go. Well, there's one more step. We have to get it onto that device. And the way we handle this is by building firmware. So firmware is basically your application compiled into our systems. And we do this using OTP releases. And EXRM, specifically, we have a plugin that's automatically included as part of the dependency chain, which will ensure that when EXRM reaches out to be able to ask for where Erlang libraries are, that we point it to the right place. and where the system files are as well, that it's pointed to the right place. That's all handled for you. Once you have an OTP release, during the firmware, mixed firmware step, we also then use squashfs tools to be able to take your application and squash it into the system. You can imagine the system to be, your Linux, like a Linux system. So we just basically marry the two together at that stage. And then we use a utility that we've provided, Frank Hunlith wrote, called FWUp, which creates a firmware bundle. And this is a little different than considering the idea of firmware images, because a firmware image has a lot of empty zero space in it. We make this really small and portable with firmware bundle files that in this case is an accurate representation pretty much of the actual space of your project. These will be about 20 to 30 megabyte files, very easily distributable. So now that we have our firmware bundle and that stage is kind of put together, we're ready to burn it to an SD card. We provide a step for you with this as well that also uses FWUp. It's supported on Mac OS and Linux and soon Windows, where you'll be able to just say mix firmware.burn, and you have an SD card in your machine. It'll automatically discover it, ask you if that's the one that you want to burn onto, and then it'll just, in a few seconds, you'll be ready to take that SD card and put it in your device and start running nerves. So what does the resulting system look like? As I mentioned before, read-only. And the reason for this is to prevent corruption on your systems. But what we do to get around the fact that we know that you want to be able to write places is you are able to split the partition into 4 different areas. By default, we have a boot section, which is the bootloaders and the Linux kernel. And then we have a firmware chunk. Now, you'll notice that the firmware chunk on the left is illuminated and the one on the right is not. We do a little bit of block magic to be able to make it so that we slate out an area on the disk and split it in half and say this is A and this is B. And we tell the partition table that which one of the 2 chunks that it should be booted into. And this makes firmware updates really easy and tolerant, because now what we do is we're only actually using 1 partition for your active firmware, empty block space for your inactive firmware, which leaves you 2 partitions to play with. Now, oftentimes what we see people doing is we'll give you an app data partition. That's read-write. And in the app data partition, you commonly see configuration information. That's usually infrequently written data that during a power failure could cause corruption to just that partition. Strategy here would be when you boot up for the next time, you just do a logical check to make sure that your database files, SQLite files are present and working before going into the further steps. And if they're not, then reinitialize them from a seed. You can then also expose an additional partition. Commonly we see an extra partition being used, let's say if you want to be able to tell Logger where to rotate files to. This is more frequently updated information, but isn't as critical as the configuration data. If you write files to a partition because that you're doing that frequently because you want to continue to log out in that manner, you don't want the corruption potential there to affect your actual device configuration. If log files go away between reboot, who cares? Redo them. So for firmware updates, as I mentioned, we make it really easy. All we do is when a new firmware update would come in using FWUp, you don't have to write the complete image every time. You can say, hey, here's some new firmware, write it to the next partition. And what we do is we stream those bits into the other area, we enable the other partition, we ensure that it works, and then when it boots up and it says that it works, we change the master boot record to point to that portion of the chunk and say, hey, you're active now. The beautiful part about this scheme is that your old partition contains a last known good working copy of your application and your system. You can always fall back. And as I've stated before, you can enable an additional partition, because we've given you 4, to be able to write into more frequently written data sets. So that's the Nerves platform. Now let's take a look at some of the frameworks that we have. To make things easy, there's some interesting areas you have to consider with Nerves, and one of which that you normally take for granted is that the network's actually there and up. It's up to you to be able to say that you want to bring the network up and how you want to configure it. We exposed some frameworks to be able to make that easy so that you can specify which adapter you want to use and what the settings are. You can choose between DHCP, static. It'll do link local fallbacks. And you'll also be able to configure your own DNS or subnets, things like that. I'm only briefly touching on this one. It's a sore subject in a way. We've been asked a lot for Wi-Fi support because the new Pi 3 has it built in. And indeed, that's an interesting addition that we want to make. Currently, we have a project that's just come out today as well that we're calling interim Wi-Fi because there's a bigger thing that we need to solve under the hood. And I only want to briefly touch on this topic, but it's something that we're working towards the future on. And that is the idea of handling system initialization. See, with nerves, the reason that your system boots up so quickly directly to your application is because, unlike other Linux systems, we basically replace common initialization like systemd or udev directly with the Erlang VM. Because we figure it handles supervision for you. It's probably the best thing around to be able to do system initialization for you. That's why it's up to you to be able to bring up networking. And in the case of Wi-Fi, things started to get a little bit more complex because now we had different utility actors that we wanted to have in place that needed to kind of know about each other, but not, and share state transitions between them. So we're working on methods of being able to make initialization easier for developers. So much like working with Phoenix routers, you'll be able to actually just state rule sets that'll allow you to dictate how different libraries will interact with each other so that you can make sure that when a network device becomes available, that it furthers down the line to be able to establish your network interface. But not only that, that when a network device becomes available, you can perform whatever user actions you also want to perform during that time. So moving on from this problem, it's hardware. We want to be able to do some real world work, right? We also have a library written by Frank that's ElixirAL. And this library allows you to be able to interact with GPIO. You can do analog reads. You can do digital input-output. You can do SPI, I2C. And in addition to that, we also have some community additions. Greg Mefford wrote the NeoPixel library. Adafruit Industries sells these extremely awesome tricolor LEDs that you can string them along for as long as you want to go. They're all addressable, and they use pretty much they use like one digital pin to be able to actually interface with your device. So from there, you can specify, you can address them individually, and you can change their color individually. You can use animations with them. It's really cool stuff you can do with those. So now that you're connected to some hardware, you're going to want to put some skin on this thing. So let's talk about some user interfaces. Well, everybody here knows that when you go to router pages or device pages, that typically these are like web interfaces that we're talking about. And what better to be able to use for web interfaces than Phoenix? Phoenix gives us so much that makes things in the embedded space instantly cool. And the structure of this we've come up with in a recent project is it felt so natural to make it as an umbrella because we wanted the ability for you to be able to rapidly prototype your interface development with your nerves development at the same time. And to handle it this way, because nerves projects are always compiled for your target, and those nerves projects may contain NIFs or ports that are then compiled for a Raspberry Pi, when you try to run that project on your host in IEX, you probably won't be loading the right binaries, and the system will get mad at you. So in this situation, you want to be able to still leverage all the great tools. You want to use live code reloading. You want to be able to see your changes happen as you go along. So what we did with this is we set it up in a way that you can make calls in. Let's say you have a web interface panel that you want to set up some pins. And those pins, that Phoenix application doesn't know anything about GPIO. It doesn't need to actually start supervisors or processes that are going to start monitoring physical pins on your computer. They're not there. So in this case, we have to take a little bit of a liberty. And we say that if you're running in dev, you should start pointing your stuff towards these stubs. And these stubs we're going to be including on our library. Conveniency that'll allow you to be able to use unit testing with Phoenix application UIs, so that way you can simulate input and output on pins, or when button presses are happening, or more complexity like actual protocols of streams of data coming in. Once it's time to go to production, well, we just swap things out. We say, all right, let's put those active pins into play, and now we link in the core, and your entire application is up and running and ready to go. This was the technique that we used to be able to rapidly prototype that product in 5 days, and here's the result that we had that the customer was enjoying. The liberties that we ended up taking were people in this realm, they don't really see this kind of real-time updating, and when it came down to it, we looked at what we pitched to them, what they were asking for us to do. And when we had to put counters on the display for when events happen, and we had to put a real-time log streaming on the display, and we wanted the clock to start counting up and things like this, well, you know, it just felt natural. We were like, well, I'm reloading the page because it's what they wanted. And I have to say, Phoenix never made scope creep so palatable. So that's some of the basic stuff. Let's talk about a few advanced things that you can get into. One of the things that comes up often is, hey, I built my system, I've got my Elixir application, but I need to be able to interact with some other files in my file system. I want to add some additional files to my root file system. Well, we expose the ability for you to do this directly. You can add a configuration option for your firmware to tell it to point to where your root file system additions are. And by using multi-target, you can actually get away with specifying this in each individual target's configuration file. So if you needed different files or different versions of files for different targets, like a Raspberry Pi or a BeagleBone Black, you can make that decision and at the assembly time. So all you do here is you point it at a directory. The contents of that directory gets merged into the actual file system, and then this happens at the time when you call mix firmware. So it's really fast, and it's not always doing it on every compile. Well, what happens if you want to change files in your root file system? A common use case here is Raspberry Pi. Well, Raspberry Pis, we have to choose which interface, which TTY we want to be able to send standard in and standard out to be able to show the IEX prompt on the device. That differs between the serial port that's on it. Most times people use a serial console cable to connect USB to connect their Raspberry Pi to see on their host computer what's happening on it. But other times you might want to be able to just plug it into an HDMI display and show the display output because there's an HDMI port on that device. So we, by default, right today, ship the Elixir, the IEX prompt, to be able to be sent out to display on the HDMI port. And a common situation is, hey, I want to use a serial console cable. So with this strategy, you'll just point the same way, root file system additions. But any files that you find that are already present on your target, like ones that we include directly with our system configurations, if you provide your own, we'll just overwrite it with the version that you provided at the time of assembly as well. In this situation, we're just showing that inside of the init conf, which is the init is the thing we replace systemd with, we can specify when the device would hang that we want to be able to have the device hang on exit, so that if the Erlang VM crashes and we need to be able to see the crash report, we can actually see the crash report without it completely rebooting every time. Good for development, not good for production. So changing root file system files is one thing. You just want to make sure that you don't do it, that if you're expecting different results that it merges, it won't. It'll actually completely replace that file. And we do all this using FWUp. I had to present this. Apparently in the Urban Dictionary, it's a cute puppy, so we had to grasp that concept and come up with a logo that looked like a cute puppy. One other thing you're going to want to do is have access to change files in the boot partition. With using FWUp, you'll actually, there's an FWUp conf file that you can replace. That in that conf file is also the location where you'd specify additional file system partitions. The sizes of those partitions, the structure, the format of those partitions. And when you add those additional partitions, let's say in this case what this is illustrating is On the Raspberry Pi 2, you want to be able to change the console output to be able to go down the a serial console cable. You can use this strategy to also replace files on the boot partition. The reason you have to do this differently is because all the files that are located on these partitions are different for all different devices. And as seen before, this is just the text example of how this kind of stuff is laid out. So this is how you would also use the fwupconf file to be able to declare additional partitions, like the log file partitions. You can see more about this by visiting the fwup GitHub page. There's extremely good documentation on all the different options you can use to make configuration changes to that. Something cool that you also want to do too is connect to remote nodes. Once your device is on the network, you can actually use IEX to be able to connect directly to other nodes. So all this cool stuff comes included today. And with that, there's still more. We're working really hard to be able to bring some great next level technology to this platform. And in the last several months, there's been a huge explosion in commits and contributions to the project. So what's ahead? Here's the future-ish. We're going to be bringing in display and touchscreen support so that your Phoenix web applications will run natively on touchscreen devices. We're also working on bringing network firmware updates, which I hear are actually done today as well. I have that in this one because there's some testing that we need to do with that. We're looking to make the development lifecycle even faster. By using serial console cables, we're looking to make it a way to be able to use code reloading on your devices during development without having to do it over the flaky network, because as we've stated before, that's not always great on everybody. We want to be able to make things always connected. We want, in that development lifecycle, the ability for you to be able to write tests and have them execute remotely on the device to verify that your hardware is working. We're looking to create some development kits, and on top of all of this, we are doing better documentation, adding video camera support, and I hear there are actually books in the work for this too. So this leads me to the statements made earlier, and that is that it's time for embedded to have its revolution. It's time for embedded 2.0. So what are we doing to change the world in this case? There's some experiments that we're running with some others in my area on how to be able to embed NERVs devices, really lightweight updatable NERVs devices in drones and 3D printers to be able to control these devices and network them together. In addition, we have several clients using things in production. We've taken a distillery and automated their entire still to be able to use NERVs for actuation of valve systems, control flow, and it's all driven from an Apple Watch. We also have Rose Point Navigation. Garth is one of the main core team members. His company ships products using NERVs. They have battle tested these things. They are rock solid and have actually wonderful experiences producing these products on this platform. So let's do it. Let's get out there and rewrite embedded. We have other people in the community that added some projects as well. Wendy's been making an automated cat feeder. And Timo's here. Right? He's been using NERVs to be able to do temperature control on fermentation for beer. So I ask you, imagine you're in an era of near infinite inventive possibilities, and you have hardware that's become smaller and more powerful, and languages and frameworks that are new and provided to be able to give you the power to invent anything that you can put out there. And it's easy. Thank you.
Thanks a lot, Justin. I'm afraid the rest of the conference has been cancelled because I need to run out, buy myself the Raspberry Pi, an Apple Watch, and set up the distillery. We have time for a few questions.
Thanks for the talk. So I have a question about Wi-Fi. So, for example, we have not Raspberry Pi 3, but even more, and we buy Wi-Fi adapter. And like when we buy it, we also buy some payment drivers.
Okay.
Is it sold now, or is it going to be sold, or what's the state of Wi-Fi drivers?
So with the interim Wi-Fi package, we've also enabled a small subset of Wi-Fi, common Wi-Fi drivers for the Linux kernel under the hood. Typically, these are the Realtek drivers. We're going to be assembling a list of all of the currently enabled ones. But if you want to be able to do, if there's a Wi-Fi driver that you have, if there's a Wi-Fi chip, like dongle that you have that enables a driver that we don't have enabled, we'd certainly work together closely with you to be able to get that added in as either a system addition or a system extension as well, which will, it'll offer the support for you. So as of today, you can plug it in using the new Nerve systems. And if it doesn't work, let us know. We can make it happen.
Thank you.
Do you have another one?
So thank you. My question is, what's the next step? What is about, let's say, Internet of Things, about a debug code or something else? So really that's different embedded devices can work together or connected to the cloud or something else.
For the Internet of Things and connecting devices and accessing this sort of debug code, that's all part of some future work we're working on. Right now, you can actually take Nerve's devices and use distributed Erlang to be able to strap them together, do node connects with them. For IoT purposes, we're invested in looking into new technologies like LoRaWAN and supporting that out of the box to be able to do local wide distributed networks. And for your debug messages and debugging your devices, the serial console cable connections for the development lifecycle, we're looking to standardize the ability so that when, just like your Phoenix or other Elixir applications, when you type like IEX-S mix and you want to be able to like play around with that device on your host connected, we're just going to do all the magic behind the scenes to be able to make the remote shell connections happen for you. So that's in the works right now. Yeah.
Hello, so I have a past in embedded C, embedded system, and I wonder, you talked a bit about toolchain and GCC. Do you support any other compiler? I'm mainly thinking about LLVM1 for Rust, or you know.
So we don't. Our toolchains right now are mainly glibc, GCC based. But like I said, we're built on top of CrossToolNG with our configurations. So anything that you can really create out of CrossToolNG, which I believe you can create LLVM ones in there, you'll be able to generate those, and using the structures that we've implemented with our toolchains, you can also out of the box support mirrored caching of those as well with our same fundamentals. So.
What level of complexity are we talking about? Your 5 days project to the market?
Yeah, so really, the device was created as a universal example of something that can be done. We made something that allowed them to be able to dynamically, through the web interface, configure pins to be inputs and outputs, decide whether they wanted to connect LEDs to them, or also dynamically associate actions to be taken when a digital pin would go high or when it would go low. So what they ended up using this technology for was to be able to monitor equipment in a manufacturing facility, and when the equipment would set an alarm off, they would make HTTP posts against their ERP system to synchronize the data with the point at which the process was at, so they could further inspect the product and ensure a quality control on it. So it was really flexible. There was a lot of great configuration that came out of it. But in reality, it didn't require a lot of low-end embedded experience because of all the frameworks and things that we give you in the project.
Thank you so much for the talk. I thought it was amazing. Just one thing, I was just interested, who's behind the project? So who are your sponsors?
Ourselves. I have a lot of hardware at home. My wife gets upset about every time I buy a new one, but so myself, Frank Hunleth, Garth Hitchens, we're all members of the core team. We have a great community of people that have also stepped up to be able to contribute code and libraries and help with testing and documentation. We could really use anybody to be able to come along and give us a pretty looking facelift on our site and some organization. Documentation is definitely one place that we were really trying to attack and bring up to speed. But currently, we put a lot of our time, effort, and money in it ourselves. We really want to see it succeed.
Cool. Thank you so much.
Thank you.